Hello, I am David Jeffrey, and in this video I shall be discussing the Ruby integration project. The Ruby project aims to evaluate indefinite integrals using a rule-based paradigm. Rule-based as opposed to an algorithmic design, which we shall discuss a bit later. An important part of Ruby is that it searches for optimal output forms. We shall be discussing that also a little bit later. A side effect of the project is that it has compiled a large database of examples and a large database of integration rules. Both of these resources stand independently of the Ruby project by itself. It is public domain, and you see on the screen the address of the website. The main author of Ruby is Albert Rich on the right of this photograph. Previously he wrote the MuLisp, MuMath and Derive projects before starting on Ruby. Here he is on Mauna Kea on the big island of Hawaii with his Hummer. Albert has been working on Ruby for more than 10 years and has amassed, as we just said, large databases. There is a test suite database with over 72,000 entries, and there's a rules database with over 6,700 rules. Quite an achievement even by itself. The rules database consists of a large number of entries, rather like the one I have selected here. You can download all of the rules in PDF format from the website. Here is a typical entry in the database. It starts off with a heading saying which integral is going to be discussed. Then we have references. Gradstein and Rijik and CRC are both well-known reference works in this field. Then we have a brief description of where the rule comes from, then the basis of the rule, and finally the rule itself, carefully numbered. Every rule has a distinct number. And notice how the rule is phrased. Firstly, we have conditions. BC minus AD must not be 0, and M must be less than -1. If those conditions are not met, then this rule is not to be applied. Then the rule itself starts with the integral and converts it into a term without an integral sign plus a modified integral. Notice that M is less than -1, so the original integral has a power of M. The modified integral has a power of M plus 1. Since M is starting off negative, M plus 1 will be in absolute terms a smaller number than M. So we have reduced the complexity of the integral by this rule. Here is a second rule. You see, again we have the heading, again the references to Gradstein and Rijik and CRC, again the derivation, and again the rule. This time the rule is a little different. The integral is expressed in terms of a closed form expression. This is a terminating entry, so a typical integral would be evaluated by a chain of transformations such as the first rule we showed, and then it would terminate with a rule such as this, in which the integral is removed entirely from the last expression. Maple can already integrate, so you might ask, why should we bother about Ruby? Well, yes, it's true that Maple can already integrate, but Ruby adds a distinctive feature to integration, and that is, we know that an integral of a function is not unique. Students are required to add +c to their answers in their first year calculus course. What is less obvious is that equivalent expressions are also possible for an integral. And what Albert Rich has done in developing Ruby is to consider for each integral the different possible expressions and to search for the optimal one. And now we shall see what this optimality is that we're talking about. And so what is optimal? I'm going to illustrate it with these 3 examples, and for that I'm going to switch to a Maple worksheet. So here we have a Maple worksheet. I'm going to start by defining a class of problems. If you look, F is going to be x to the n, 1 plus x to the 12th, and we're going to consider this class of integration problems as n varies. Let's first start with how would a student of calculus evaluate an integral such as this? Well, the textbooks tell us to use partial fractions. Maple can do this for us. For n equals 5, I'm going to ask for f to be expanded as a partial fraction decomposition. And there it is. The terms are not sorted by powers, but that's how Maple is. You notice that each term in the partial fraction decomposition is in a very simple form. None of them has an x in the numerator. So when I integrate this, I can integrate it term by term very easily. And there is the integral. This is in fact how Maple already does the integral, and we can prove that by just asking Maple to do the same problem, and we get the same answer. Now the interesting point is, how does the size of the integral grow? And so that's what I've written here. For n goes from 0 to 10, evaluate the integral. So in the output, we're going to get one line for each integration as n increases. To fit it all onto the screen, I have to reduce the size a little bit. And now I'm going to evaluate that. And there are my integrals. We start on the first line, n equals 0, n equals 1, n equals 2, n equals 3, etc. And so you see we get this tree-like structure with the integration growing with the value of n. So down here at the bottom, we have the integral for n equals 10. I shall assign that to a variable f10. I shall check that everything is okay by simplifying the derivative of f10 with respect to x, and we should get our problem back again. And there we are. Now what is optimal? Well, I'm now going to compare this f10 with another expression. Look at this very simple expression, x to the 11th over 1 plus x to the 11th times 11. I'm going to differentiate and simplify that expression. And you see I get the same result. So that means I have two equivalent expressions for the integral of x to the 10th over 1 plus x to the 12th. The version f10, which contains 10 terms, and the version f-ruby, which contains 1 term. Here I have simplified f10, and you see that even after it has been simplified, it is still much longer than f-ruby. So what is the connection between f-ruby and f10? Well, let's simplify the difference between them. And we see that they differ by a constant. Well, we have already said that an integral is only determined up to a constant, and here there is a difference. So what happens if I take this constant and I add it to f10? Well, I get the simple result from Ruby. The point is, Ruby has gone to the trouble of investigating all possible integrals of x to the 10th over 1 plus x to the 12th and discovered this special case which is particularly simple. And this is the difference between the algorithmic approach, which has a single algorithm that works for a whole class of functions, and something like Ruby, which looks at every special case separately. And that is the advantage of Ruby. Anytime there is a special case where a particularly simple exception to the general rule exists, Ruby will attempt to return that special, simple case, the exception to the general rule. So that's the first type of optimality that we're talking about, an optimality based on size of expression. Here is a second type of optimality. Here is little g, which is going to be the expression we're going to integrate, and I'm going to consider two possible integrals for it, g1 and g2. Let me just verify quickly that indeed each one differentiates to the problem at hand. Well, that g2 doesn't look obviously the same as the integrand. However, if I subtract the two of them, they simplify to 0. So indeed, both g1 and g2 are valid integrals for little g. So then we ask the question, which is better? I think most people would probably choose g1. After all, it contains only a single arctangent instead of two arctangents, and the argument of the arctangent is a polynomial with integer coefficients, whereas the arguments of the two arctangents contain this square root of 7. So it would seem that G1 is the better result. But let us try and use these two results to calculate a definite integral. Here is a plot of G, the integrand. Remember that the integral is the area under the curve. So G1 and G2 are both expressions describing the area under this curve. This curve is G. Notice that the curve is always positive and it is always continuous and smooth. Therefore, any calculation of the area under the curve has to be a positive area. We're going to calculate the area from -4 up to 2. Clearly we have a positive area under the curve. We're going to use the fundamental theorem of calculus that says we can calculate the area under the curve by calculating the integral at 2 and subtracting the integral at -4. We'll do that first for G1. And you see we get a negative answer. How can we get a negative answer if the area is so clearly positive? Well, to answer that, we're going to plot G1, something we've not bothered to do yet. And we see that G1 is actually a discontinuous function. If we look back at G1, we notice that the denominator of the argument is equal to 0 if x equals plus or minus the square root of 2. So how can we use G1 to calculate the area under the curve? So in order to evaluate this integral, we're going to have to do it in pieces. We're going to have to go from 2 down to the square root of 2, from the square root of 2 down to minus the square root of 2, and then to -4. And I've done that here. I've evaluated G1 at 2, then I've evaluated G1 at the square root of 2. Since the value of G1 at the square root of 2 is ambiguous, I've taken a limit from the right. Then I've taken a limit from the left. Then I've moved to minus the square root of 2, taken a limit from the right, and then a limit from the left, and finally evaluated G1 at -4. After I do all of those calculations, I get this quantity here, which is the positive answer that is required. Now I want to compare that with doing the same calculation with G2. I plot G2 and I see that it is a continuous function, and therefore I don't need to bother with all of this intermediate calculation. I can simply apply the fundamental theorem of calculus to the interval from -4 to 2. So I just eval G2 at x equals 2, eval G2 at x equals -4, and simplify. And there I get the same answer as from the more elaborate calculation from G1. Our conclusion is that although G1 is more attractive, it is more compact, it contains simpler constants than G2, in fact G2 has a very good argument for being the optimal solution because it makes the actual calculation of definite integrals much easier than with G1. So optimality is not so obvious. Our final example is the integral of 1 over x. If I integrate 1 over x, Maple tells me log of x. Many teachers of first-year calculus say, couldn't we get log of the absolute value of x, which is what we see in our textbooks? The trouble is that by the time you get to third or fourth year and you do complex integration, the form log of the absolute value of x is no longer useful. Unfortunately, Maple has to choose one form, and it chooses the form that continues to be valid when you get to third and fourth year. So at the moment we have been implementing Ruby for Maple, and there are a few features of the integration which are not so obvious. The first one is the integration rules that I showed you early on all have an integral being transformed into another integral. And it seems that's the main purpose of Ruby. But in fact, if you think about how integrals are done, many times you are not actually working with calculus. A lot of the time you are just doing algebraic manipulations that prepare the integral for the calculus step. We have already seen that in this talk. Our first example, the first step in the integration, was a partial fraction decomposition. So therefore a large number of utility functions have been written to prepare integrals for Ruby by algebraic manipulation. After we've got those working, then we'll be able to go ahead and start to bring in all of the integration rules in Ruby that provide these optimal antiderivatives. So keep calm, keep integrating. Thank you very much.